All right. Today we have our esteemed guest, Leonardo Alt, who's here to give us an overview of his latest project, PowdrVM. Leo, the stage is yours.
Thank you. Yeah, thanks for the invite. Yeah, I'm going to talk a little bit about just a high level what Powder is, and then we can jump into some code, run some examples and demos, depending on what the audience feels like. I'm going to do the presentation first. Feel free to ask questions anytime. I'm only on one screen, so I won't see the chat or the call at the same time that I'm presenting, so just please speak up if you have a question. All right, is my screen all right?
Yep. Perfect.
Cool. All right, yeah, thanks again for having me. My name is Leo. I'm working on Powder, which is a modular stack for ZK VMs. And just to, I feel like a lot of people here probably know a lot about ZK already, but just to kind of set the stage, what exactly is a ZK VM? Well, here we're using the term ZK, which means zero knowledge, but we're not really doing anything necessarily related to zero knowledge. We're using the scalability aspect of these proofs to do certain things. So what we're interested in here is a part that is about verifiable computation. We want to prove that a program runs on some input and produces some output, and you can convince the verifier that this statement is true, where the verifier can be convinced of that in a much faster way than just re-executing the program, which can be pretty heavy. There was a way a couple of years ago, it's still the case that people use tools like Circom or Xergates to write ZK circuits, which are fixed in size, and they really have the shape of arithmetic circuits where you can really see it, the inputs as wires, and then it gets into the circuit where you have the gates, and the gates can be multiplication or addition, and in the end you can get one or more output wires. The difference from that to ZK VM is that a ZK VM is also a program, and it can also be implemented as a circuit. The difference is the input of the ZK VM is a program. So you don't only have a fixed circuit which represents a program P and takes its inputs and dynamic values X, but now the program is also an input. So you want to be able to run a program, a generic program on a generic input, and prove that you got some specific output. The advantage of this approach is, again, the same as we see with traditional virtual machines in computation, is that this scales proofs to any program that runs inside that VM. So you don't have to write every single program in circuit anymore. If you have a program that compiles to the VM that's supported now as a circuit, then you can make proofs for these programs. There are quite a few existing ZK VMs already. This was mostly pushed by the ZK EVM space, which has quite a few implementations already, but there is also implementations, ZK implementations of traditional VMs, such as RISC-V, which is not as traditional, but it works with traditional programming languages, LVM, WASM, and some more custom ZK-friendly VMs that are used mainly in Ethereum L2 projects. The reason why we've built Powder, or we started in the first place, was that we felt like in the ZK VM development context, the tooling is still kind of lacking, and I think it still is. And what that leads to is that custom ZK VM implementations, such as some of these that I mentioned before, the way you implement these ZK VMs, some of the problems they have, they're pretty difficult to audit. They're pretty hard to change. They require a lot of people to build it and to maintain it. One big problem is that most of them are prover specific, which causes a lot of vendor lock-in, and they become hard to reuse. So if you have a new proof system, which is extremely common in the ZK space, then you basically have to rewrite a lot of the ZK VM in order to take advantage of a new proof system or some new ideas that have come up after you've built your ZK VM. And well, the advantage that they have is obviously that's what's available. a lot of these decisions were made because that's what existed 1, 2, 3 years ago when these things started to be built. And we see already a lot of different trends when building zkVMs. And the performance of these systems, they're very specific to proof systems, they're very low level, so you can get a lot of performance from these. But of course, this starts to lose its point over time when you get compiler optimizations and these kind of things, and also different proof systems, combinations of proof systems, etc. in new zkVMs. So what's the idea behind Powder as a zkVM toolkit? So Powder does not have a built-in VM. So Powder is not a VM itself. It's a framework, it's a compiler where you can build zkVMs. And the idea is that currently the way programs are written is in specific assembly language, which comes from the proof systems usually, and look like the left-hand side. And with Powder, the idea is that you can basically write high-level programs, and these programs can also be VMs, but even writing the VMs themselves in Powder assembly is still a lot more maintainable and high level than if you're using, I don't know, Halo 2 or Starks or any other air arithmetization directly with the proof system. So again, Powder is a compiler stack where you can define different zkVMs, accelerators, and circuits, and so on. And these, and you can make proofs for whatever programs compile to these zkVMs that you support. And the idea is that you can abstract away low-level constraints and proof of complexity from the implementation of the VMs. And this allows for a lot of modularity, a lot of acceleration of critical components. It enables a lot of automated analysis, which is very common in the compiler world, where we have compiler optimizations. Not in specific to the ZK space, you can have non-determinism checks, form verification, and in different compiler passes with static analysis and so on. The idea is to maximize the developer experience without compromising performance, and we'll talk more about this later. And the main idea being that it has to be easy to build, to test, to audit, to modify, to maintain, and so on. This is the general architecture of what Powder looks like. So everything you see inside the middle square is contained inside Powder, except for there's a caveat where this Powder, as a RISC-V LLVM, Wasm VM, they are not built in Powder. They are written in Powder assembly using Powder IR. So you can basically define any VM that you want, and that becomes an input itself to the compiler, and that gets compiled with the program that you want to make a proof for. And this means that you can use any high-level programming language, C++, Go, Rust, JavaScript, Solidity, etc., that compiles to any VM that has an implementation in Powder assembly. And you'll see what it looks like later. The cool thing about a compiler pipeline is that usually you have a lot of steps. And in Powder, each of these steps, at each of these steps, you can stop, you can look at the current artifacts, you can look at what the Powder assembly looks like at this point, you can inspect it, you can even optimize it by hand or using different tools, and you can plug it back in and say, okay, continue now from here. And then this has compiled to Powder Pill, which is a low-level constraint language that looks a lot more like what a proof or arithmetization would look like already. And here you have generation of fixed columns of witnesses and some more optimizations. And when this gets compiled, you can do the same thing. You can look at it, you can change it, you can optimize it, and then put it back in. At this point, Powder connects to different proof systems, such as Halo 2, eStark, and Supernova, to then finally give you a proof. So the idea, the architecture idea behind Powder is very similar to what LLVM does for traditional programming languages, where you can have multiple programming languages. You can use C++, Rust, and so on with LLVM. And all of them get compiled into an IR, an intermediate representation language, which here in our case is Powder ASM or Powder IR. From here on, you have a single pipeline that goes through the entire compiler and makes use of all the features. At the very end, you can then open up again, where in LLVM, this means compile it in different architectures. You can compile to x86, you can compile to ARM, you can compile to RISC-V, to MIPS, and so on, or more embedded systems. And in the Powder case, this means making ZK proofs with different proof systems. And, excuse me, one basic question, why would I use Powder? Do I need it at all? Do I not need it? And yeah, when would I need it? So we see two main use cases for Powder. The first one is that you're zkVM builder, and that's how we actually started. Making tooling for people that are building zkVMs. This basically enables these people to focus on a high-level architecture of the VM, the design of the VM, and potentially the proving part as well, leaving all this compiler architecture in the middle, just managed by Powder. So this makes it really easy to write, audit, maintain, and verify the implementation of a certain VM and makes the proof straight at the other end. The other case is, we can, of course, the special case of the first one, I just want to make proofs for Rust programs or for C++ programs and so on. In this case, Powder is in this very specific case, it's just a drop-in replacement for compiler stack. And in this case, it becomes very similar to RISC-0, SP1, zKLVM from Mill Foundation, and so on. One example that we've maintained so far is the RISC-V front end, which basically implements the RISC-V 32 IM, A, and C instruction sets. And it was written basically 300 lines of Powder code. And Powder automatically synthesizes witness, constraint, and so on. And you can get proofs for Rust no STG code. And you have different VMs being written. And again, these are not built in Powder. They can be built with Powder. They're part of the standard library. But they don't have to live within the compiler itself. And anyone can write these. And this is one example of what the compilation process looks like. So here we have some Rust code that uses a normal Rust library, tinycatchhack, to prove that you know the pre-image of a certain hash. So you have a public hash that's input, which is here, and then here's our pre-image. We hash it within the circuit, so to say, the program, and then we assert that they're the same. This gets compiled to LLVM with the RISC-V instruction set, which you can see in the middle. This then gets transpiled to the Powder IR, and then from here on, it just goes to the Powder pipeline. The Powder IR language is a language that still resembles assembly and programs, where you have the notion of machines. And in these machines, you can have registers, and you can have instructions, and you can have functions. These are all the built-in constructions that you have in its IR, and you can use them to specify different VMs, which have registers and instructions, for example, and you can use the function parts to then specify the programs that you want to make proofs for. You can also write lower level machines. For example, this is a machine that does some arithmetics. And here you can see lower level constraints, lower level constructions like columns, which is very specific to proof systems then, to optimize the proof time, for example. And then you can use these machines in this VM setup without losing the modularity, without losing the encapsulation aspect of optimized VMs. Then finally, this gets compiled to PowdrPil, which is a constraint language which has columns. I mean, now it actually has a lot of things we haven't released yet, but it is a very basic Fibonacci circuit, which it just has an error table that gets basically sums X and Y at every iteration. And I'm not going to go through details of every single operation here, but this is just a low-level constraint language, which has arithmetic gates like this, but it can also have lookups and permutations. One other cool thing is that we can have a standard library, which is much bigger now than what I'm just showing here. And what the standard library gives us is optimized circuits. And then we can actually use these optimized circuits in Rust. So we can say, actually I have that in the next slide. So this is just, this is still just Powder code. And here I have a Poseidon for the Goldilocks field machine, which is part of the standard library. And then I can just use this machine and then have a test VM here, which has a bunch of registers, and then I just run some tests in this VM, and that's just a test that it's very simple to use the standard library. And then, as I was saying before, you can also expose these accelerated optimized circuits to Rust, and then use them in Rust when you're making proofs for Rust programs using Powder. So this is one example, just a very simple example of how the same library. So, for example, I have a Poseidon sponge library, which is just the same Rust code. I don't have to change it at all. The only thing I have to change is the bottom primitive that if I'm making proofs with Powder, then I'm going to use the Powder accelerator. If I'm not using Powder, I'm just going to use my normal Rust Poseidon and then just run tests with it. Other things you can do with Powder are recursive proofs and the so-called continuations for large Rust programs. Usually, if you do use RISC-V or MIPS or any of these, or WASM or these traditional VMs, your programs are going to be very long. And they're much longer than what we would like to put in a single proof. What we have to do then is break down these these execution traces into chunks or segments that are manageable in single proofs. So then you take, for example, an execution trace that has 10 million instructions or cycles in WASM or RISC-V, and then you can break it down into 10 segments of a million. Then you make a single proof for each one, then you do some recursion, and finally get a single proof out of these. With all of these, this is basically an ZK EVM implementation just by using our EVM, which is a Rust EVM implementation used by the Wrath client. Within Powder, this is just a task that runs a transaction, and this simply uses the REVM library with Powder. There's lots of applications that are kind of obvious with the tooling like this. If you just want ZK RISC-V or ZK WASM, you can just build a VM and then prove execution of any program that can be written in languages that compile to these VMs, and you can make ZK proofs for them using multiple provers and potentially even VM implementations. ZK VM is also massively interesting for the Ethereum ecosystem and the L2 space, which still cares a lot about EVM. We can support EVM in two ways. We can use ZK RISC-V or ZK MIPS or ZK WASM and an existing EVM implementation such as Geth or REVM or EVM1, or we can actually write specialized and optimized ZK VM in Powder assembly, similar to how we did for RISC-V. And this should be a lot more performant because I don't have any of the VM overhead. Other use cases that are fun, just like custom VMs like Valida and Maiden, which we still want to implement in Powder assembly, and the opposite of L2. So, because when L2s make proofs, they're interested in EVM computation, but L2 data. And there's a lot of projects that are actually interested in L1 data. So, for example, storage of smart contracts into L1, but arbitrary computation written in Rust or Python, for example. So a lot of these things are possible at the same time, and they're generic enough because we use a compiler stack. Basically, what that means is that all the features I've just showed, they apply to all VMs. So all the optimization, static analysis, accelerators, stdlib, ZK continuations, recursion, and different provers, they apply to every VM. And the VMs are not built in, they can be implemented by anyone. And these features would just work for these VMs. So this was the presentation part. We can jump into some code, but feel free to ask any questions. Let me see if there's anything in the chat. All right, so no questions yet. Yeah, okay, so as input, is there any specific part that people are interested in seeing? Because otherwise I'm just going to show some programs and go through some ideas.
Leo, maybe just a general question before you get into the weed of code. So for two aspiring ZKVM developers, let's say, why would we need more than one ZKVM? What would be a differentiating factor between two, for example? Because if we can create ZKVMs through using Powder and it abstracts away everything that goes into it, why not just have the ZKVM and just optimize the hell out of it? What do you see as a differentiating factor that different people will create different ZKVMs to target, for example?
I think, yeah, that's a very good question. I think one thing is different VMs are different things and they just have different specs. So I think you could argue that very well for general purpose ZKVM proving. You can say, okay, I can either focus on RISC-V, or I can either focus on MIPS, or I can either focus on WASM and then choose one, and then support that VM, and then optimize the hell out of it, and then get a pretty solid, pretty good ZKVM, right? In that case, what you're losing is the possibility for custom VMs, which is still a pretty big market in the Ethereum L2 bridging space. So for example, a lot of VMs, they have to be customized because of privacy. So if you look at the way Aspect works, or like Alio, or I think these are two of the main privacy ones, right? Or Maiden, for example. Maiden actually does enable privacy. Their VMs are very, very different from the likes of, again, RISC-V or WASM. So you do need to customize. And then that means that if you're starting from WASM VM and you want to have MyDen VM or some privacy VM that you invented, you basically have to write it from scratch, right? And this includes all the circuit, all the accelerated circuits and so on. This is just like one very basic one that I can give you concrete examples, because if you look into, again, MyDen, Nasdaq, and so on, the VMs are very, very different from what you see in general purpose VMs. The other aspect is just VMs that are more performant in the ZK setting. So if you look at Cairo or the ZK Sync, VMs that are much more optimized for the ZK setting. So if you have a compiler architecture that compiles to those VMs, you're going to have a lot more performance and even potentially UX features such as new crypto libraries and so on, which if you do via general purpose VMs, you might lose. And I mean, maybe one day it's all going to be possible general purpose and we don't need anything customized anymore. But currently it's still the case that a lot of the use cases do want customized, or just like they want to write their own VM for specific needs. And the last one is like ML. There are a few sort of VMs and circuits that enable performant and usable machine learning features that people can make proofs for. And this is particularly important in the ZK-ML niche space. So this is just my take on it. Any other questions? All right, so you can actually start. Can you read my screen still?
Yep, we can.
Cool. So I'm just going to open some tests. So what I'm going to show you now is basically like a very simple VM and a program. Actually, yeah, so this code here, we can start with the function. So basically this is the program. We want to do something. We want to prove that something happens over some input. So what is this part of the program takes in Powder assembly code, and Powder assembly is very simple. You can do assignments to registers. This is a register, this is an assignment, and you can have labels, and you can refer to those labels somehow. You can call instructions, and you can have some commands, like this is an ugly command for prover queries, where you can ask the prover for private information that goes over the bus. But that's basically it. Which instructions can you call? That's up to you. Every instruction that's called here in the assembly code and every register that is assigned to and used has to be defined in the VM. That's what I meant earlier. There's no built-ins. Like you have to define instructions that you use, and that comes with the VM implementation. So what is this code doing? So this code is telling the prover, okay, give me the input in index 1, and then we'll put it in count. This program is basically doing a sum over a list of numbers. Then we have our start part of the function. We compare count to the check register. Wait, where is this check? No, this is it. Oh, sorry, we don't compare. We compare count to 0. This is a jump 0 instruction. So if count is 0, we jump to check, to the check label. Let's say we had 3 here before. So it's not 0, we count as 3, we go in here. At this point, we ask the prover, okay, give me then the next input. So before here we read the size of the input, the length of the list. Now we're reading the list itself. So we read the next number in the list. We sum with A, which starts at 0, and then we accumulate over A. Again, we're just summing the numbers in the list. We decrement the counter, we go back to start. There's just a loop. We check count again, now it's 2. We read it again, we go on until the list is done. At the very end, we then ask the prover, okay, what did you think the sum was? Because what the prover wants to prove is, I know the sum of this public list of numbers, which is obviously a very simple thing to do, but it's just a toy example. And this is where the prover gets to say, okay, this is what I think the sum is. We subtract from A, because the result should be 0 then, if the prover is right. And we assert that A is 0 to test that the prover is right, and that's it. So if this program works, the prover is proving that they know the sum of a certain list. So this is just the programming part, which you can write any program with these registers and instructions. What do instructions look like? We have 4 instructions here. Assert 0 just says that something is 0. Just ignore. This is a bit of a low-level sort of inline assembly tricks. Decrement count, we just say the next count is current count minus 1. Unconditional jump, we just say the next PC is the argument that's given. And the jump 0 instruction basically tests whether the given value in X is 0. If it is 0, we jump to the label L. If it's not 0, we increase the PC by 1, which is a common behavior. Besides that, we just need to declare some registers, and that's basically it. So this here is a VM, and this here is a program written in that VM, using that for that VM. And we can basically implement, we can write any program that we want, as long as they use these instructions and these registers. And we can make a proof for this by where is this test data as a simple sum? So let's say we have a list of size 3, the numbers are 1, 2, 3, and the sum is 6 that I'm claiming. Okay, so far this only generates the witness. We can then say prove with something. And this is going to create a proof. I have to remember how long this takes because the program, okay, it's done. So now we have a proof. This proof here then proves what we basically just said, right? And I think we can also, yeah, this should be enough for the proof. Any questions? Right, so
if I am, sorry, just a quick question. So for the RISC-V VM that was created, that is basically machine RISC-V, and then if someone is proving using that VM that I created, it will basically be injected that main function into the previously created VM.
Yeah, exactly.
Right?
Yeah. Yeah, so this code here, what I'm just showing has nothing to do with RISC-V. This is like a custom VM, right?
Yeah, just using it as an example, yeah.
Yeah, so that's what I was going to show now. So if you want to do RISC-V, for example, let's take an example and then see the generated code. So RISC-V. So we can use the same idea. So we want to get the length of a program, read a program, compute the sum, and then ask for the prover what did you say the sum was, and then assert it the same. So this program is doing the same idea, proving a list, proving that you know the sum of a list. We can do it like this. It's not test data anymore. So what it's going to do now, this is compiling my Rust program to LLVM assembly, which is this. Now it's transpiling to Powder assembly, which is going to output in a second. Yeah, now it's compiling to, sorry?
Cargo Rust pill is used as a subroutine in Cargo Rust, run Rust, right?
Yeah. So Rust is going to do some extra steps of first compiling the Rust code to LVM assembly, then compiling to Powder assembly, and then it can call the pill compiler part. But then it does it internally. It doesn't use the CLI then for that. Yeah, so this step takes a bit longer because this is a much bigger program now. But I can already show you what it looks like. So we have some, so this is the generated Powder assembly code. It looks a bit unindented, but yeah. So what you see here, this bit here, machine until here, which is, wait, not here. Where's this one? Okay, my indentation is messed up. But, so first we have the definition of the machine, of the RISC-V VM. So the RISC-V VM has a bunch of registers. has these other registers, which represent the RISC-V registers. Then we have a bunch of instructions, and you can see the instructions are like assembly. So we have a jump instruction, we have some branch function instructions, we have some arithmetic instructions, and these instructions, they use machines that already exist in the assembly library. So for example, the binary and the shift assembly library machines can be used here to then compute these instructions for RISC-V. Some other instructions, and instructions are defined by means of constraints, using registers or other columns if we do low level. And yeah, this is where it ends. So it's basically 303 lines of powder assembly, including comments and everything, but of course also using existing standard library machines that can be audited separately and so on. But yeah, as you said before already perfectly, this is the VM definition, and this VM will be the same for every Rust program that you run. Actually, from the language side, we still have to split the VM from the program because these are independent things. And then the program itself comes in here. We have this function main, and ignore all this debug data. And you can see here, this is the assembly program already in Powder assembly, transpiled from the LLVM assembly, which is, yeah, like some of these, for example. This would be the LLVM assembly generated by LLVM in Cargo. And then we take this, transpile to Powder assembly, which is this. And from this point, we can then take some inputs and make proofs for it. So this gets compiled directly from the Rust program that you want to make a proof for. And the VM definition is static. We wrote this by hand. It gets injected by the compiler, it gets combined with the Powder assembly program that then gets transpiled from LLVM. But all these definitions here are handwritten. It's 300 lines of code, it's not much. And you could do the same thing for like WASM or MIPS or EVM, for example. EVM, I think, is more complicated just because of all the weird things it has. But yeah, so this part is static, gets injected by the compiler, combined with the compiled Powder assembly function, and it just goes from there afterwards. So here you can see that, so we compile to RISC-V, then did some compilation steps, compiled to Powder assembly, compiled to Powder pill, optimized it, removed a bunch of stuff, then computed the witness, which is this and here, and from this we can go make a proof. This program will be pretty small. I can also run a high-level RISC-V executor here. Actually, one cool thing is that at this point, we already have the compiled Powder assembly, so we don't have to use the Rust tool anymore. We can just say pill and then just use the assembly directly. And this will just bypass a bunch of compilation stuff. This is what I meant with like, we can always stop and start at any point the compilation step. Some are easier than others, but this is a pretty easy one, meaning we don't have to recompile anything from Rust to Powder assembly. At this point, it's doing some witness generation, and then it's ready to make a proof. One thing you'll notice is that this program is actually quite small, so I can do just like, instead of generating the witness for, it's not printing. This option here just runs a high-level RISC-V assembly executor. I just want to, wait, let me quickly change something to show you one thing. Yeah, here. I think this should do it. So you see that it has 434 cycles only, meaning that it started running function main, and only 400 instructions were required until the end of a successful execution. The thing with ZK proofs, at least so far, a lot of the ZK VMs, the proofs are actually monolithic big tables. So what the arithmetization looks like is you have a bunch of columns. Each column is like a register, and each row is time. So you're just going through time, running some instructions, and this is a witness. This big table is just a witness. You take this witness, you give to a prover, the prover is going to turn it into polynomials and so on. This has a fixed size, and you have to know that in advance in most of the current zkVM techniques. And the fixed size we chose here is this, which is 2 to the 18. So even if we only need 434 rows in this big table, we still have to provide a table of size 262,000 to the prover. So that's why, for example, if we run the full witness generation, it gets low at some point because it's not doing 400 rows, it's doing 262,000 rows. So this is also, and then when you make a proof, the same thing. And it's actually, there's a lot of tricks with recursion and different proof systems, but it's actually kind of tricky to combine different columns of different sizes, or really only use a size that you need. And there are different techniques we are currently implementing. Some of these that hopefully will help a lot with performance, but currently you do have to rely on a big table where everything has the same size, and things can get pretty slow because of that, even if your runtime is actually small, like 400 lines of code. Any questions there?
Looks like we do have a few in the chat.
Right. Let me go there. Let's check them. What does arrow X mean? And then assignment to a register. Yes, the arrow itself is the assignment. The X in the middle is a bit of a, just a syntax hack for now. It's an optimization where all assignments from right-hand side, left-hand side have to go through the X assignment register, and this acts is like a bus. So basically, forcing assignments to go always through a bus can lead to a lot of optimization later on. That's the main reason we have the weird X in the middle. Is summed up as in Powder specific or standard LLVM output? It's Powder specific, but it's automatically transpiled from LLVM assembly. So the flow looks like Rust LLVM assembly, Powder build proof system. Yes, that's correct. The max value a register can take depends on the underlying curve of the proof system. What's the detachment? Yeah, it's a very good question. So all the values in the registers in the columns here are of all the types. They're a specific field element of the proof system we want to use. It's configurable. You can say, for example, I mean, this is finished, but it doesn't matter. I could say, for example, use Goldilocks, which is what we use by default because it's very handy for RISC-V 32 bits. And this is required for the east-wide proof system. But if I want to use Halo 2, for example, then I have to switch to the BN field. Yeah, so the assembly code stays the same, and it should work because we have a lot of invariants in the way we wrote the assembly instructions that should guarantee that every register by implementation is within a 32-bit range, which is what RISC-V operates over, the RISC-V 32 instruction set. But language-wise in Powder, the register can actually hold a full field element of whatever you configure here. How about MLIR support? Which MLIR do you mean here? You mean more from like the OCaml side of things, or is this a machine learning thing? Can you just clarify? Oh, the LLVM one. Yeah. So there's no support directly in Powder because we can transpile it to Powder assembly. And I think for us it makes more sense because so Powder assembly has specific things like pill and columns and field elements, and it's these things that we do need for the proof. So I guess it could be supported as a transpiler. I think it could make more sense than just a language. And I guess this is already If you use the LLVM compiler, then it might be supported already, but then you have to choose a target VM, right? So the language itself is only supported if you have a target. But yeah, it's a good target to aim for. Yes, it's hello to KZG from BSE. How does original code complexity translate after using Powder? I believe certain operations are way more expensive, so the complexities change non-uniformly. Yeah, that makes sense. So things like curve operation, signatures, or even just like shift operations, we don't have that in the proof system, right? So how do we implement shifts? Like we have multiplication, we have addition, but even multiplication itself, I'll show you a tricky thing. Which, okay, this one is already fixed. But if you implement, like how do you implement multiplication here? This is also a relevant thing. So you can assume you have two 32-bit numbers, right? And the multiplication fits the Goldilocks field. So if we say, okay, I want to multiply Z and W, and I want to split the result, and then so Z is 32 bits, just a comment, W is 32 bits, and then I want to split, and then I want to compute Z times W, which is 64 bits, and then I want to split this into X is, yeah, let's go with this, lower and higher 32 bits. So basically what we have to do, we can say, okay, R equals Z times W, and this is a 64-bit number, and then we can do a byte decomposition, and then do a byte decomposition again. So that here you can see that like B1, B2, B3, B4 are the 4 lowest bytes of R, and then you can do the same thing for Y. Let's see if Copilot does it. It's not doing it. But let's say we can do the same thing for Y, so that we just increase how before. And this continues. And then finally, we say that R is plus. Okay, Pilot's not feeling helpful. And so on. Okay, so what are we doing here? We're multiplying Z times W, we get a 64-bit number. We say, okay, this 64-bit number is split into 8 bytes. R1 to RB1 to RB8. Then we say, okay, now we're going to use these 8 bytes into different windows. X is going to be contained of the X is going to be the actually this should be the same thing. X is going to be the lowest 4 bytes, so B1 to B4, and Y is going to be the higher 4 bytes, so B4 to B8, right? Does anyone see the bug here? I'll give you 20 seconds. And okay, actually one detail. We are on the Goldilocks field, which is 2 to the 64 minus 2 to the 32 plus 1. 2 properties the Goldilocks field has, or one property is that if you have 2 field elements A and B, then you can do, actually if you have 3 field elements, A, B, C, you can do A times B, A plus B times C, and D is still fits in the Goldilocks modulus. So this is why this is really optimized for 32-bit VMs, because it can do an add mul with 3 field elements. Sorry, this is 32 bits. Yeah, you can do 3 operations, you can do 2 operations plus and mul on 3 32-bit numbers, and this still fits the field element, so it's really useful for optimizations. So and here you can assume Z is 32 bits, W is 32 bits, and you want to multiply Z and W, and yeah, with the lower bytes in X, higher bytes in Y. Where's the bug? Let me see if the chat found the bug. Shouldn't the left-hand side and right-hand side be replaced in line 2 of our function? Line 2, where? As in the assignment. So yeah, so in here, this is not assignments, these are constraints. So you can also do like this. So the assignments are only in the function notation, like here, which is assembly. Inside instructions, we have constraints. So the equals is just like is equals to, it's not an assignment. But yes, overflow is a problem. Why is overflow the problem? Because we're doing a byte decomposition. And byte decomposition in field elements is a super scary thing. Because here, R is 64 bits, and it can use the full range of the 64 bits. So it may be the case that R is bigger than the Goldilocks modulus. If that's the case, if R is bigger than the Goldilocks modulus, there are 2 possible byte decompositions for R. One that is under the modulus, and the other one that overflows the modulus, which is bigger, that satisfy these constraints. Even though they look fine, you're doing byte decomposition, I'm attaching the bytes for X, attaching the bytes for Y. But yeah, so you can have overflow here, and you can basically prove then that some malicious X and Y are the result of multiplying Z by W and then doing the byte splitting. So if you're writing ZK things, watch out. Overflow, especially for doing byte decomposition, bit decomposition with field elements, you should really, it gets complicated. Like we have a full machine in the same library called the split Goldilocks machine, which does a safe byte decomposition by always keeping track if we have overflown while doing the byte decomposition, which is something you have to do. If you don't have any other assumptions you can rely on to know that overflow doesn't happen. If overflow may happen, which is the case here, you really simply have to check. So this is a full pill machine, which is not very big, it's like 6 lines of code, without the comments even less. But that, yeah, you have to keep track of the value to check if you have overflown or not, and then just not allow the overflow. I guess in most cases that's what you're interested in. I don't understand how R can overflow if you just said let me check again. Yes, so wait. Yeah, I explained it a bit in the weird direction. So if you have the honest case where this is the case, then R shouldn't overflow. But what the prover can do, because these are output values, the prover can say, here are 2 malicious X and Y, such that the byte decomposition works, and R ends up being overflow in 1, even though it's not the result of the multiplication, it's the overflown version of the multiplication that still satisfies the constraints. So it goes the other way around. So if you have the honest case, where you just compute the witness how it's supposed to, it's a multiplication, it will be under the modulus. But because the prover is computing the witness, and a malicious prover could set whatever x and y they want here, they could choose a malicious byte decomposition that satisfies all of these assignments, and this will end up being the overflown R. Does that help? All right. Yeah, and getting back to the other question, how does the original code complexity translate after using Powder? Blue certain operations are way more expensive. So this is something that, like, what I just said is more on the security side, right? Because it's more just like, there is more complexity in multiplication than just multiplying two numbers, right? You have to check for overflows, and then it ends up being more costly because you do have to have those checks and so on. Other things are bitwise operations. We also have a full machine that does bitwise operations, and these use lookup tables. And it's also not as trivial as in a VM in a context that has these things, right? And then, of course, if you're in Rust, and for example, the example that I showed earlier, actually in the slides, so tests, so we have the sketchup test, right? And it uses tinysketchup, which is a Rust library that computes sketchup. If we do this, it's going to spend, I don't know, hundreds of thousands of rows. For example, we can actually check. Cargo run Rust. And here we don't need this. And these are pretty costly to do in the ZK version because Ketchak uses a lot of bitwise operations, so ANDs or and XORs, and not sure if ORs exactly, but ANDs and XORs. So if you try to support all that from native Rust to a prover, it's going to be very costly. So what you would usually do in this case is write a standard library machine, which actually we're working on the Ketchak one at the moment, but to show you have the Poseidon one, which implements the hashing in a lower level using PIL. And then this gets exposed in Rust, and then you can use it in Rust to hopefully alleviate the performance hit. So this is 18,000 rows to do one Ketchak in Rust, which maybe doesn't feel a lot, but it's actually a lot if you want to compute Merkle trees or L2 states or these kind of things that require a lot of it. Let's say it's a Nova-proof system. I write my circuit in Rust, which has got non-quadratic constraints. Do I develop a custom VM to handle R1 yes, or does PowdrPool handle it on its own? Pool doesn't have to have quadratic constraints only. When you go to proof system, then it depends. So if you write higher degree constraints in PIL and you go to Halo 2, it's fine, nothing happens. If you try to do that and go to eStark, then it's not going to work. But it's fine because PIL has what we call intermediate polynomials, which is abstracted using just variables. And this gets replaced accordingly. So PIL itself doesn't care about the degree of constraints, but it is something that we have to think about when connecting PIL to the backends. And maybe I can actually give you a quick glimpse of what the backend integration looks like. So if you go to backend, no, actually, yeah, it's here. No, it's in Halo 2. So here you have this approver library, which has some data structures that we wrote that have some PIL relevance, and then most of these functions are just calling functions in Halo 2. So we just load some the verification key, for example, and the parameters, the setup parameters for Halo 2, and then you just call approve, right? And there's one layer we have to do, which we call the circuit builder, which takes a Powder data structure, which is called analyze. It's called a PIL analyze PIL, and outputs a powder circuit here, which implements the Halo 2 traits, I think. Yeah. So here you can see that we make a powder circuit data structure, and then we implement the Halo 2 circuit trait for the powder circuit, and then that's basically it. So the whole file has like 400 lines of code, including some helpers and stuff. So it's really not complicated to convert powder pill to Halo 2, but because their composition is very similar. So in pill we have constraints, we have arithmetic constraints, we have permutations and lookups, and that's exactly the things you get in the Halo 2 API as well. Same thing for eStart. But if we want to do Nova, for example, it changes a lot. So we actually, someone from PSC started writing Supernova backend for pill, but we never finished it because the abstraction is just quite different. And I'm a big Nova fan. I actually wrote a lot of Nova stuff. And I still want to have a version that makes use of Nova and recursion, which I haven't found a full setup for it yet. But yeah, I'll have to think a bit more about how the abstraction goes if you want to support Nova. Because then, do you do recursion on every instruction? And do you do recursion on whole columns? Like on subsets of columns, we do recursion on chunks. Like it's. I find it a bit hard to find the right abstraction for Nova or Supernova or Hypernova here. Yeah. Okay, so we do powder pill CCS. Yeah, exactly. So I think doing CCS would be a good first step because that allows us to go to Hypernova or to, what was it, CycleFold or any of these new ones that people have been working on. So I think this would be a good first step, like powder pill to CCS, however CCS is defined. And then from CCS, we can think about, okay, how do we prove that the program we want to run is we want to make a proof for is indeed the program we had in the first place? How do we distribute the memory over all the columns that we need access to? How do we do aggregation, all those kind of things? But I agree with you, CCS is a good start. Yeah, I saw this Nexus implementation kind of recently, and I haven't dug much into it yet. But yeah, it sounds fun. CCS I can't remember. Does anyone remember what CCS? Constraint something system.
It's customizable constraint system.
Right. Yeah. Thanks. Yeah, so we're at the hour. I think we had some spare time for questions as well. But yeah, feel free to shoot. Otherwise, I think I've shown the bits that I wanted to show, at least in this like overview talk. So yeah, thanks.
Yeah, thank you, Leo. I have a general question about the idea of using ZK co-processing, meaning not co-processing as in axioms, etc., but as a way to combine or synthesize handwritten circuits, let's say Halo 2 circuits, so that the optimization you do is in the tool chain of Powder as opposed to optimizing the Halo 2 table itself. Because one thing I noticed that, let's say you have two circuits written in Halo 2, and the proof is output circuit 1 times output circuit 2 is equal to something. That's the proof. So you get a Halo 2 table, right? And then it may not be optimal, so you optimize it in terms of like columns and rows and all of that. So I'm wondering, does it make sense for someone who is doing that now to say, okay, no, I'm going to take the two circuits into the Powder toolchain and then optimize differently there, because there is more than one layer that I can optimize. Does that make sense? And have you had experience doing this or thinking about this?
Yeah, I mean, I completely agree with that approach. And yeah, I think this is something we've been really aiming for. So basically, instead of writing Halo 2 circuit, you'd write a pill circuit. And there are a few reasons why and why not, I guess. The first reason why is that if you do that, then you automatically get circuits compiled to different proof systems, not only Halo 2, but for eStark and whatever other proof system we support, or even CCS, right? If we have CCS, we shouldn't be too far off PowdrPil. Then if you write like a standard library circuit in Pil, then you get Halo 2, eStark, and CCS. The second thing is that it's higher level, right? It's not like you're not writing constraints by hand in Rust. It's still like a full-fledged language. It has generics, it has closures, it has types, and the low-level constraints, right? So it's much, much easier to read, in my personal opinion. And to get an audit, it's like in a few hundred lines of code, you can have like a full machine or even full different machines. I mean, we call everything machines, but coprocessors or accelerators, whatever. You can have full accelerators doing curve operations, doing signatures, doing Merkle trees, hashes, all these things in not that much code. And you could, for example, audit one once, and then it just stays in the same library, right? And so you got these two advantages, which kind of combined work well. And the third one is basically automated optimizations, right? So if you have a compiler, there's a lot of optimizations you can make that are just automated, right? And not only from the compiler, there's maybe someone comes up with some other crazy optimization tooling, and then you can also use that. So it's much easier to combine these efforts in a DSL like this. So you just get a lot of advantages from doing this. The disadvantage is, of course, that there might be cases where it's hard to do automated optimization, that you would still find handwritten things that are better, but that can still be done. So we can take all this Pil stuff and then write it in Pil and then compile it to the the Halo 2 version of this. And at that point, if someone wants to say, okay, I'm a Halo 2 Rust expert that can optimize anything, this person can still take a look into the Halo 2 generated code and say, okay, I can still optimize this further by hand. So I think the two approaches can still be combined, where I think one is just more scalable, right? If you're writing in Pil, it just compiles to different things. You can do compile optimizations, you can do audits and so on, so it just scales a lot more. But you still have the flexibility of looking at the generated Halo 2 code and saying, okay, I can optimize this by hand, and I'm fine with that. To explore more on the security side of PowdrVMs, does one have to have a deep understanding of the Powder stack to audit a VM, or even a circuit developed using the stack? Yeah, so that's a really good point. I see two different things here. So the basic answer is no. You don't have to have deep knowledge of how Powder works under the hood on the compilation stack and so on, because I think the code is just very readable. So when you read assembly code, like any Powder assembly that let me just open it again. Like this, for example, this is very readable. You have to know what things mean, which is normal in any programming language, right? So you have to know what these things mean. It's not trivial. You have to know what these things are. You have to know what this weird assignment with an X thing is. But you don't have to know how the compilation steps work or any of this. You just have to know the semantics of the language and what it means to do things. And same thing in Pil. This gets compiled to Pil. And if you want to write an STD circuit that does Poseidon again, for example, you have to be able to read this, right? This 100 lines of code. You have to know the closures. You have to know what does a zip do, what does a map do, what are commits, what are constants. You know, like you have to know how the language works. As a similarly how to, if you're auditing Solidity work, you do have to know how the compiler does some things, meaning what are the semantics of Solidity constructs that become EVM instructions, right? But you don't have to know all the internals of the compiler, and it's very similar here. On the other hand, it's also important. So if you're doing audits on circuits, on ZK circuits, you could do audits on assembly files or pill files without necessarily knowing how Powder works, just knowing what the language means. On the other hand, it's also important to ensure that the compiler isn't introducing any bugs, right? So it's a different thing. Then it becomes more like a compiler audit, a Rust audit, because the compiler is in Rust, an architecture audit, which has it's a very different scope to ZK audits. So I would say both things are obviously extremely important. And I think the former ends up happening the most because it's more users writing circuits and assembly code. But eventually, the compiler should also go through one or two just like big security reviews to make sure it's not doing anything unsafe. But these usually happen in a lower frequency because at some point it's going to be stable. It's not going to change that often. Similarly to the standard library, when you write these things, they're going to be audited once and they won't change much. So these are things that you have to audit, but they happen less frequently than auditing circuits that people write for their own applications. Why can't I just audit the original Rust or C code? Exactly, yeah. So this is a really good point of reusing Rust libraries, right? So if I'm making proofs for Ketcheck, so if I, again, use the Ketcheck, where is it again? Where's 5? If I use the Ketcheck crate, this is my entire program, right? I'm verifying that I know the preimage of a hash. I'm proving that I know the preimage of a hash. This here is trivial. And let's assume the tiny Ketcheck library has been audited and verified before. So I'm pretty confident in this. So I don't have to audit the circuit. Here you're trusting the compiler, right? So as long as the Powder compiler doesn't have any bugs in code generation and parsing and whatever, then you should be completely safe. But that's what I meant with, if the compiler is stable, it should also be shown that it is safe. But I completely agree with you. If this is a massive benefit of just being able to reuse code, right? Be it Rust, C, or even Powder Pill code from the single library. In terms of swapping one backend for another, let's say from KZG to IPA or Fry, how easy is that? Is Pill completely abstracted from that? Yeah, it's pretty abstracted from that. The assumption that it has right now is that it works for Plonkish authentications. So whichever proof, so the commitment scheme doesn't really matter. As long as the whole proof system together, so basically both the IOP plus commitment scheme, as long as the tooling for proof systems that you want to use support blockish authentication, meaning this big table with potentially lookups, then it should be fairly simple to translate Pill to it. We're actually going to make it even simpler because we have a new iteration of Pill coming up, which relies on Plonkish plus challenges, basically air plus challenges actually from the prover API, but does not require the prover to have lookups and permutations. That's going to be implemented in Pill itself as a standard library function using the challenges from the prover. So it reduces the requirements for us to be able to integrate to new provers. Then we could, for example, integrate with Winterfell or Plonky3 or whatever in a much, much easier way because we don't have to rely on the prover providing lookups and permutations, because then you're also relying on what they use to implement lookups and permutations, which arguments. Whereas if you can implement the arguments themselves in Pill, then you can do a lot of nicer things. Is there any app or benchmark for the Powder stack just to get an insight of how much VM overhead Powder reduces? Well, it actually increases the VM overhead in a way because, especially if you do, well, yeah, that's actually a good point. It reduces the VM overhead if you write the specific VM in Powder assembly. If you use the RISC-V front end, for example, then it introduces overhead, right? So this is the same with, like, again, RISC-0 or SP1 or Nexus or any VM that is general purpose, you will have a VM overhead. If you write the VM directly in Powder, then it should, I agree with you, reduce the overhead. I don't have any benchmarks right now. I do have a repo where I run the Ethereum state tests through RVM through RISC-V and Powder, which is here. But this currently only does it via Rust, so the overhead is pretty big. But I do want to write some things that you said. So what we're actually going to start writing soon, not exactly a benchmark that compares the whole overhead of VM in Powder or VM in Rust, but the accelerators. So we're going to have Rust code that uses ECDSA, for example, then implement the CSA in PowdrPill, and then compare the two, right? So this will give one idea of of the overhead reduction of the accelerators. But I do want to write an experiment, like you were saying, with the full EVM machine. So we're going to write the EVM in Powder assembly as well, like we did for RISC-V. And that's going to be a full implementation in Powder. So there's going to be no RISC-V whatsoever. And at that point, we can have a very clear benchmark, right, of running the same transactions, like Ethereum state tests, for example, or an L2 block over Powder Rust, RISC-V, or Powder EVM directly, right? And even compared to other VMs as well that support either RISC-V or WASM. Will auditors become less relevant once the KVMs become efficient and production ready? How long will it take if yes? It's a good question. It's really hard to predict these things, right? Potentially one day it's going to become less, not less important. It's always going to be important, but maybe the market just won't be that big, right? If we're all using Rust or C++ or JavaScript code that has been audited before, it's just the surface much smaller, right, for things that we have to look out for. But I think we'll always need accelerators. I think without accelerators, it's going to be, maybe one day it's going to be, yeah, if the provers get 1000x faster, then who cares about accelerators? You can just do everything native, including CDSA and so on. But it might take a while, yeah. The access bugs come from cracked things combined together in a buggy way. Yeah, completely agree. You are bound to implement some vanilla Rust, compile through Powder, compare benchmarks to the current Halo 2 implementation. Yeah, this would be really fun. Yeah, but one thing we also want to do is, so currently we do have lookups and permutations built in PowdrPill, and they just use the Halo 2 arguments from the Halo 2 library. What we want to do as benchmarks is implement the arguments in PowdrPill, generate all the constraints with the challenges, and then give that to Halo 2, and then see how that compares to the Halo 2 implementation of the arguments. I think it should be the same, but it's going to be a fun benchmark as well.
Yeah, this is something we are doing throughout the fellowship, Leo. We are issue these bounties just to get everyone interested and excited about doing things like this. So
nice.
If you would like to draft just a one paragraph description of something you would like to see, around this, just to give you context, we are auditing the Suma code base, which is zkDApp written in PSE Halo 2.
Yeah, sounds good.
So the logic of the zkDApp is simple enough to be implemented fairly quickly in vanilla Rust, for example, and then compiled, and so we can see and compare the benchmarks basically.
Yeah, Rust RISC-V versus handwritten Halo 2, that's going to be a big overhead. But yeah, it's going to be fun to see how bad it is.
Yeah. This was amazing, Leo. Thank you so much.
Do we have any more
questions?
Thanks
for all the questions. Lots of great questions there.
Yeah. All right. Thank you, Leo. Thank you for agreeing to do this presentation. I think this was such an insightful presentation. So, yeah, thank you.
Yeah, for sure. Thanks for having me, and feel free to ask questions on GitHub or on our public matrix channel. I'm happy to run through some ideas and potentially collaborations.
Yeah, sure. Thank you, everyone. Have a good day. Bye bye.
Thank you. Bye.